Hey everyone, this is it. This is the review for magnetic fields and magnetic forces. So we start off in chapter 26 with the magnetic force on moving charges and current carrying wires. We saw that the force for moving charge depends on how fast the charge is moving, the magnetic field strength, and that it is charged. A neutral object like neutrons or an atom that has equal positive and negative charges feels no magnetic force. And what does that magnetic force do to us? Well, magnetic forces cause centripetal forces. Since it's a cross product, remember, put your fingers in the direction of the velocity. You curl your hands into the direction of the magnetic field. Your thumb gives you the direction of the force. That was our right hand rule. If it's an electron, you can use the left hand doing the same exact thing. Since these forces create centripetal forces, charges start to make circles as they go into magnetic fields. So they can pass in helix shapes if they don't perfectly go perpendicular to the magnetic field. They can form tighter circles depending on the speeds and the strengths of the fields or the charge. UVB equation applies to just single charges. So we said that a wire was a bunch of charges moving all as one. So subbing out the drift speed for charges in a wire, we came up with the force on a current carrying wire, which was Philb. I, L, cross B. You do the same thing there. You put your fingers in the direction of the current element, the I, dl, curl into the magnetic field, and your thumb tells you the force that a current carrying wire feels in magnetic fields. We saw wires jump out of magnetic fields or be pulled in to magnetic fields based on this force. We looked at scenarios like the velocity selector, where we were trying to fire charges and have them unimpeded by a crossed magnetic and electric field. So remember how we solved velocity selector problems, making the magnetic force equal to the electric force? Once it passed through the selector, the mass spectrometer was a region of large magnetic field, and we saw charges arc in the mass spectrometer. Based on how large the ion was, we knew the speed of the material coming into the mass spectrometer because of the selector, and we were able to figure out what ion and isotope we were dealing with. Then we put current through loops of wire, and we saw that if we have a loop of wire with a magnetic field, we get torques. And the torques depended on the number of turns we made in that loop, the current, and the area. We cross that with the magnetic field, and you get NIA cross B. Or, of course, a cross product is dealing with the sign. But then we said that NIA is really what we call the magnetic dipole moment. So that tells you where the north pole and the south pole are pointing for that loop. So as long as the magnetic dipole moment is perpendicular to the magnetic field, the two magnetic fields will try to align with each other, and that causes torques in the wire. And the last thing we did in that first chapter was the Hall effect, where we had a bar moving through a magnetic field or current running through a really wide strip. We saw charges separate, similar to what the velocity selector did, and based on that charge separation, it would set up this Hall voltage. So that voltage was able to tell us how fast the conductor was moving through the magnetic field or help us solve for unknown magnetic fields. So once we did a bunch of problems with magnetic fields in the first chapter, the second chapter wanted us to figure out where magnetic fields come from. And we found that magnetic fields came from moving charges. So from that, we used the Biot-Savart law. The Biot-Savart law is written there as dB mu 0 over 4 pi I dl cross r over r cubed. In the notes, I know I have it as r squared because I had that r up there as a unit vector. But I guess the way that AP is writing it here is that they have r as just an actual vector. R divided by r cubed is going to give you r squared. And this was essentially Coulomb's law for solving for magnetic fields around current wires. The other right-hand rule we had was to figure out where the magnetic field direction was. You put your thumb in the direction of the current, and you curl your hands to make the magnetic field. So we did magnetic fields along infinite lines using Biot-Savart. We did the magnetic fields around hoops of wire and tried to find the magnetic field at the center of the hoop versus off-center of the hoop. We put two wires next to each other, and we saw that the wires would either repel or attract based on the amount of current you throw, based on the forces you feel from Philb. Each wire creates its own magnetic field, and those magnetic fields will interact with the currents in each wire, causing the wires to either attract or repel. Remember that it's following Newton's third law, so each force is going to be equal and opposite. We did magnetic field superpositions, where you had to figure out what the total magnetic field was at a certain location in space. So to find out the magnetic fields from more complicated things like solenoids or toroids, we tried to apply Gauss, but we put Gaussian surface around permanent bar magnets. We found out that the total magnetic flux was 0, meaning we can't have a monopole. Gauss kind of proved that there's always two poles to magnetic fields, a north and a south, but it didn't help us calculate the magnetic field strength, and that's where Ampere came in. Ampere took the magnetic field dotted with the length, and that equals mu0 times the current that passes through that flat area. Now with this, we were able to use Amperian loops rather than Gaussian surfaces to solve for magnetic field strengths. And then we dove into the atomic level for magnetization and these magnetic domains in permanent magnets or paramagnetic materials or even diamagnetic. Which brought us to our last section. Now that we know where magnetic fields come from and we know the forces that magnetic fields exert on each other, we wanted to see if there was a connection between magnetism and electricity, and that's where electromagnetic induction came in. And the first thing we had to focus on there was magnetic flux. Magnetic flux was B dot dA. This time, instead of the area being a surface area like Gauss, it was going to be a flat area for the area of a loop or whatever shape you make. So from changes in magnetic flux, we were able to determine Lenz's law. Lenz's law told us the direction that induced currents would want to flow. They're going to try and resist the changes in flux, or you try to maintain the original flux that you already had. Faraday said, well, then if there's a current, there must be a voltage associated with that. So Faraday's law said that the induced voltage was equal to d flux dt. And remember that if there's multiple turns, you have to multiply by how many turns, so n d flux dt. The negative sign there was just to represent which direction. I said, worry about the magnitude and let Lenz's law tell you the direction of the induced current. Since that is a voltage, remember the voltage also equals electric field times displacement. So you could set Faraday's induced EMF equal to E dot dl to solve for the electric fields that push those charges through the wires when there's a change in flux. We looked at motional EMF, that was the bar sliding along magnetic fields, and we created eddy currents and magnetic drag. Just because we have a change in flux and now we have a current in that magnetic field, don't forget that that magnetic current is now going to feel the magnetic field as well and create drag forces. So we talked about the velocity as a function of time. We looked at changing flux in not just changing magnetic field strength or areas. What if we change the angle? So we found in the generator that if we rotate a hoop through a magnetic field, it will also generate EMFs at a particular rate, at a particular frequency. And just like capacitance was something that told us the charge per unit volt, in this case we have the inductance of a wire telling us the relationship between the magnetic flux and the current that passes through a solenoid. One way to solve for inductance was flux per amp, or you can see that the induced EMF is equal to the inductance times the change in current. So the inductance, we said, acts like a resistance to changes in flux in your circuitry. From that, we were able to find out that there is magnetic potential energy in the magnetic fields based on 1/2 Li squared. So as long as you know the inductance and how fast current is flowing through your circuit, there's energy that's in that magnetic field. And we went through many examples of the RL circuits when we were energizing and de-energizing those coils, where the coil wants to just maintain flux, whether it has it or it doesn't have it. So it can act like an infinite resistor when it resists that change in flux, but as soon as it is used to the flux, it no longer fights the current and now just acts exactly like it was created. It's just a wire. So it becomes pretty much no resistance after a large amount of time. And if we hooked an inductor up to a capacitor, we saw there was an oscillation back and forth like we saw in simple harmonic motion, but this time the motion back and forth was between a capacitor charging and an inductor gaining current and gaining magnetic flux. Those are the topics that are being covered in all of magnetism. Maxwell we covered for one chapter where we saw the connection between electricity and magnetism, creating electromagnetic waves traveling at light speed. So these are topics that will be tested on. Good luck and happy studying.